Good evening. Today we are going to see the second problem of design, and in this we will go for single angle section. So this is lecture number 13. So now we have step 1, we have given data. So we have given that is service load is given 100 kilonewton. So we have step 1, given data. So we have factored load 1.5 into 100 equal to 150 kilonewton. L is given 1790 millimeters. Then we have 2 bolts and hinge connection. Then we have to go step 2, selection of section. Selection of section. So now length is very less, 1.79 meter. So we can go FCD on higher side. I assume FCD 90 Newton per mm square. If length is 2.5, then go 80. If length is 3 meter, then go 70. So we can consider FCD between 60 to 100. As length increases, you have to go on a reduction of FCD. Then area required, P upon FCD. So we have P 150 into 10 raised to 3 and FCD we have 90. And from this we will get 150 divided by 90, 1,666.67 millimeter square. Now we will take angle 90, 90, 10 millimeter. Then we have step 3, properties of section. Properties of section. We have given A 1700 mm square. Then we have R VV, that is 17.4 millimeters. So now we require these two main value. Now knowing this, we have to go step number 3. So we have step 3, design compressive stress. First before this we have to go classification. And this classification is as per table 2. So we have B by T is equal to D by T because equal angle section. So 90 by 10, 9 less than 15.7, and B plus D by T, 90 plus 90 by 10, and that is 18 less than 25. And as both conditions are satisfied, section is semi-compact. Section is semi-compact. Now we will go step 4, buckling class. Buckling class. So for except beam, for all rolled section, we have buckling class C. We have this from table 10. Then we have step 5, design compressive stress. Now we cannot use tables because tables are not allowed by IS code to find this value, design of compressive stress. Though some books are given this value, but we are not going to use. Now we have to find lambda E, which is known as effective slenderness ratio. Sometimes in examination question asks determine effective slenderness ratio. So 7.5.1.2 K1 plus K2 lambda VV square plus K3 lambda phi square. Now K1, K2, K3 we have table 12. K1 we have K1.7, K2.6, K1.7, K2.6, and K3.5. And then we will get lambda E is equal to root of 0.7 plus 0.6. Actually, we have to find lambda VV and lambda phi. So lambda VV is equal to L upon RVV divided by root of pi square E upon 250. Now we will find value of root of, which is required for both, pi square E upon 250 equal to root of pi square into 2 into 10 raised to 5 upon 250. And then we will get this value that is equal to pi square into 2 to the power 5 divided by 250 and root of this 88.86. So now you have to keep in mind this value always, need not require to calculate in exam. So we will get lambda VV that is equal to L we have 1790 divided by RVV we have 17.4 divided by 88.86. And then we have this value 1.15. Then we will find lambda phi, which will be B1 plus B2 upon 2t divided by again root pi square E upon 250. And then we have this as 90 plus 90 divided by 2 into 10 and divided by 88.86. And from this, we will get this value lambda phi, that is 0.1. And then we will put this value 0.7 in lambda E, 0.7 plus 0.6 into lambda VV, 1.15 square K35 into 0.1 square. Now if we will calculate this value, we will get this value that is equal to 1.24. Knowing this value, we can find phi 0.5 in bracket 1 plus alpha lambda E minus 0.2 plus lambda E square. And from this we will get 0.5 into 1 plus. Now for buckling class C, we have alpha 0.49 and that is imperfection factor from table 7. And then we have alpha 0.49 lambda E 1.24 minus 0.2 plus 1.24 square. And now calculate this value, which will gives me value of phi, and that value I got as 1.52. And knowing this value 1.52, I can find value of FCD, and we have FCD is equal to Fy upon gamma mo divided by phi plus y square minus lambda E square to the power 0.5. And if we will substitute 250 divided by 1.1, value of phi we have 1.52. So we have 1.52 plus 1.52 square minus lambda is 1.24 square to the power 0.5. And if we will calculate this value, we will have this value 94.3 Newton per mm square. And we have last step, that is step number 6, design compressive strength. So design compressive strength. As section is semi-compact, so we have to actually write over here, we have section is semi-compact, therefore AE equal to 1700 mm square. And therefore we have PD equal to AE into FCD. AE we have 1700, FCD we have 94.3. And from this we will get this value 160.65 into 10 raised to 3 Newton equal to 160.65 kilonewton greater than factorial load 150 kilonewton, and therefore safe, and therefore provide angle 90 10 millimeters. So this is all about your single angle. So be careful with single angle. And now we will stop here only. So this is all about your single angle section.